Samtec has developed a modern and user-friendly environment called SamSev Field. It's very well suited to the creation of models, including multiple mechanisms, but also to the creation of reduced models of flexible parts, as shown in the chapter on SamSev 4 wind turbines FEA. SamSev Field is also a very user-friendly tool to post-process results, both in terms of animations as well as curve plotting. Let's name a few features that make our GUI especially user-friendly. First of all, data are usually assigned directly to CAD models, unless only meshes are available. These data are input via intuitive, dedicated dialog boxes, and can be stored in libraries and reused on demand. In short, our GUI combines flexibility and efficiency in one single environment. Let's now explain in more detail how a gearbox should be built. Let's start with the planet carriers. The first step in building a gearbox would be to reduce these parts to superelements, as illustrated in the following video. This brief demo shows the steps in building a superelement. First, import the CAD geometry. Then, assign the needed data. In our case, the behavior and the material data are enough. The material can be imported directly from the library. The data related to superelements should then be defined. These are called retained nodes and will eventually define the degrees of freedom that still exist after reduction. The retained nodes in our case should be the connections with the pins, the input and output shaft, and the planet carrier bearings. Then, once the CAD is meshed, the computation is launched after defining the number of dynamic modes that should be included in the superelement. An indication on the frequencies linked to these modes is available after computation. As you can see, creating such a model takes only a few clicks and maximum 5 minutes in real time. Planet carriers are eventually responsible for the motion of a set of gears. This set is made of a sun gear interacting with several planet gears at the same time. The latter eventually interact with the ring gear. All these interactions can be defined using just one macro. One simply needs to define the different gears involved, and then the contact properties, which are very similar to the ones used to define a simple two-node gear element. The last panel to fill in is the definition of which wheel interacts with which, according to which contact properties. Then the whole assembly can be immediately visualized for a first check. Now that we've seen how to define the planet carrier and the different gears, we should talk a bit about how to assemble all this. SamSev Field comes with a helpful feature that's called parts. Parts are submodels that can be stored in libraries and later assembled into a larger model. So a gearbox should be created following this philosophy. Create parts for all subcomponents like planet carriers, pins, and so on, and then assemble them. The complete model is therefore the sum of the parts plus some data defining the links between them. A gearbox is usually made of several stages. This fits the part concept perfectly, and it follows that a gearbox model should be defined as an assembly of parts, each of them being a stage. Since parts themselves can be made of parts, a stage should also be built as an assembly of parts. In this case, a planetary stage is made of pins and bearings linking the pins and the gears. This assembly can be duplicated twice. When the different parts already exist in a library, building a stage is carried out in a few clicks and in a very short amount of time. Then pinions are defined using the macro with the pins as support. Next, the planet carrier superelement can be added and linked to the pins. And finally, both the input and output shaft can be added. Using this technique, parallel stages as well as planetary stages can be built and assembled to create a complete gearbox. Now that we've seen how to build and submodel a gearbox, The last part of this presentation will explain the kind of results that can be obtained using SAMSEF4 wind turbines gearboxes. First of all, it's important to stress the fact that no matter what software is used, the accuracy of the results will always depend on two things: the amount of detail in the model and the accuracy of the input data. This second point leads us to the conclusion that the best way to obtain accurate loads is to integrate the gearbox into the global model and run the computations directly there. When this is not possible, one can also do it the more traditional way, that is, apply forces and torques to connections with the rest of the structure. However, in that case, the coupling is missing. How to integrate a local model into a global one is explained in the chapter dedicated to SAMSEF4 wind turbines structural dynamics. Results available after transient analyses go further than the usual ones. We can of course plot the usual displacements of any node, forces and torques applied on shaft and pins, or contact forces between gears, and then post-process them. For example, we might wish to plot trajectories of gear centers. But since we can use a relatively high level of detail in our models, we can also predict more advanced phenomena, like the clearance and bearings taken up during emergency stops. For instance, you can clearly see on this graph that the bearing goes from one end of the clearance to the other, and then back at the very moment when the emergency stop starts and the generator is disconnected. And when zooming on the first peak, which can be seen in most curves, like the torque in the input shaft here, one can see the short time range during which the torque is and remains zero, corresponding to the amount of time taken by the gear teeth to move from one end of the clearance to the other. Obtaining these results requires a high level of accuracy in the data and of details in the model. As a result, these are one of the main reasons why several companies have chosen to use SAMSEF4 wind turbines today to achieve their design needs. It's now time to conclude our presentation on gear elements. We've seen in this presentation that SAMSEF4 wind turbines gearbox comes with two major features that are making the life of design engineers much easier. First, a state-of-the-art gear element to predict the dynamic behavior of geared systems quickly and accurately. And secondly, the SAMSEF field GUI with its submodeling feature, which enables the replacement of large parts of the structure, like a complete stage or planet carrier, by other ones with just a few clicks. Design engineers can use separate environments for both gearbox modeling and its use in global models, both dedicated to their specific tasks. Thanks to that, they can really focus on their design job and not have to learn how to model gearboxes in an environment that's not suited for them. Nor will they have to try to simulate the rest of the turbine in a gearbox-dedicated piece of software. The last and probably most important point is that the high accuracy of results that can be obtained, coupled with the ease of use of this package, makes it possible to have better designs and shorter design cycles.